Hello, everybody. Welcome back. Today we're going to be starting a new unit, Unit 3, which is all about the properties of substances and mixtures. And I need to tell you that Unit 3 is the most heavily covered unit on the AP exam. The biggest percentage of questions on the AP exam will come from Unit 3, so it's definitely an important one. So let's get started. So as you all have come to know my videos, I always start a unit with a factoid, and I think this one is really interesting. I'm on the East Coast, so this equivalent of this loud sound would be as if a volcano erupted in California. We would be able to hear it on the East Coast, which is just incredible. So we're starting this new unit today, Unit 3. And what we're going to be focusing on today is all about intermolecular and interparticle forces. And we're primarily going to be focusing on liquids and solids, mostly because they have a lot in common. They are very incompressible, whereas gases are very compressible. We don't talk about interparticle forces in gases because typically the particle distances, the distances between the particles are so far apart in gases that there's really not much to talk about. But liquids and solids, lots to talk about. Liquids and solids are very incompressible, which means their densities don't really change all that much with temperature. And their similarities are due to how their particles are held together. And so that's what this subunit 3.1 is all about. We're going to be looking at mostly what are called intermolecular forces. So it's important for us to remember the difference between the prefix inter versus intra. Inter means the forces between something. The prefix intra, like if we say an intramolecular force, we're talking about a force between two atoms or within the molecule. So for example, if I was having us examine the connection between those two atoms, that would be an intramolecular force, whereas an intermolecular force, I'm not drawing this very well, would be an attraction between two molecules. So intra is within a molecule, inter is between. And if you will remember back from Chem 1, there are three intermolecular forces. London dispersion forces are the first type. They are the weakest interaction, the weakest attraction between two molecules. Dipole-dipole attraction has sort of an intermediate strength. And then, of course, hydrogen bonding would be the strongest. And we're going to look at each one of these individually. And let's start with London dispersion forces. First of all, guys, it's important that you recognize that all covalent compounds, all compounds between nonmetals experience LDFs. However, before I go any further, I want to talk a little bit about how you word things on the AP exam. A lot of students are tempted to say things like, this particular molecule has LDFs or has dipole-dipole attraction. Please do not use that word. I'm going to underline the word that is better. Please use the word experience. If you say a particular molecule has London dispersion forces, that sort of implies that you think that those forces might be within the molecule rather than between two molecules. So please don't use the word has. Rather, use the word experience when you're talking about intermolecular forces. So, as we said, all covalent compounds experience London dispersion forces. Now, if a molecule is nonpolar, and we've talked about that before, meaning a molecule that does not have an overall charge on one side or the other, that is, London dispersion forces are the only force that a nonpolar molecule experiences. London dispersion forces are also experienced by noble gases as well. So what is a London dispersion force? If a molecule has no overall charge, how can there be attraction between molecules? And I'm going to use as an example this molecule that we are all breathing in right this very moment, oxygen gas. Completely nonpolar, okay, meaning it experiences London dispersion forces as the only intermolecular force between one oxygen molecule and another. So I'm just drawing another one next door. Now, here's the thing. Electrons, guys, are not static, okay? Electrons have movement and motion to them. So at any particular point in time, a nonpolar molecule might just be slightly polar, but only for just a second, only for a moment. Meaning the electrons are just ever so slightly pulled on one side of the molecule versus the other, which gives the molecule just a slight imbalance in charge, but again, just a slight imbalance and only for a moment. That's what that term in front of us, instantaneous dipole, is referring to. It's polar, but only for a split second. Well, we're going to see that in, another oxygen molecule. And what that ends up doing, if that oxygen molecule on the right is just slightly polar for just a split second, that can induce a slight dipole in the molecule next door. And I'm going to change colors once again. And what we get is a slight attraction between the negative end of one molecule and the positive end of another. But again, it's a very weak attraction and it doesn't last very long. That's what a London dispersion force is. So when you get this instantaneous dipole, it can induce another instantaneous dipole in the molecule next to it. That's what a London dispersion force is. Now, some nonpolar molecules are more easily induced into that momentary dipole than others. And there's a word in front of you, very important vocabulary word, highlight it in your notes, polarizability. That means a molecule's ability to be drawn into that instantaneous dipole. And here's the deciding factor. The more electrons a molecule has, and I'm not talking valence electrons, like total electrons. The more electrons a molecule has, the more polarizable it is, the more likely it is to be drawn into that instantaneous dipole. So if you are comparing two nonpolar molecules, and one molecule has a higher molar mass than the other, higher molar mass is going to imply a bigger molecule, one with more electrons. So what? So what does this mean? If a molecule is larger, has more electrons, more polarizable, that means that the London dispersion forces it experiences with its neighboring molecules will be stronger than the London dispersion forces experienced by a smaller molecule. And again, so what? Well, we're going to talk about this a little bit more. That's going to lead to things like higher melting and boiling points. It's really, really, really important that you guys recognize that when you go through a phase change, you are breaking intermolecular forces. You're not breaking covalent bonds. So the greater the strength of those intermolecular forces, the more energy is required to melt or boil, so you're going to have higher melting and boiling points. And we're going to look at some examples of problems involving that very concept in just a second. The last thing I want to say about London dispersion forces, you may, depending on which textbook you're using, you may see this term van der Waals forces. That's a little bit of an old-fashioned term, but it means the same thing as London dispersion forces. It's really not used too much anymore. So let's talk about the second type of intermolecular force, dipole-dipole attraction. Remember, the term dipole is just a fancy word for polar. So dipole-dipole forces are experienced by molecules that are polar, okay? And you can see right here those symbols that we've seen before, and that those symbols are indicating, hey, this is a polar molecule. Dipole-dipole attraction is the attraction between the negative end of one molecule and the positive end of a neighboring molecule, between molecules. And the more polar the molecule is, meaning if a molecule has, let's say, a very electronegative element on one end, it's going to attract those electrons within the molecule more strongly, more polar. That's going to lead to stronger dipole-dipole attraction. So let's look at an example problem. And if you want to try this one on your own, you can. I'm going to talk through it, but if you'd like to pause the video now and try it on your own, go for it. I'm going to talk through it though. It says, the structures of ethane and methanol are shown below, and then they tell us that one of these two molecules is a liquid at room temperature. The understanding is that the other one must be a gas. And it says, based on their structure and intermolecular forces, predict the molecule which is the liquid at room temperature. Okay, so we're given their formulas, and the one on the right, we're given its structure. All right, so things that determine whether it's a solid, a liquid, a gas at room temperature are determined by the strength of their intermolecular forces. So let's figure out what intermolecular forces are at play here. Ethane on the left, if you were to draw that out in full, you'd see that it is completely symmetrical, non-polar molecule. So it will experience London dispersion forces only. Guys, on the AP exam, please don't abbreviate LDF. Make sure you write out London dispersion force. Okay, but ethane is experiencing London dispersion forces only. Let's look at methanol. It's covalent. So it is definitely going to be experiencing London dispersion forces. But I can also see that methanol is polar, which means that it will be experiencing dipole-dipole attraction. I'm just going to write dip-dip. Please don't write that on the AP exam. And it says, based on their structure and intermolecular forces, predict the molecule which is a liquid. Well, I can see that the methanol is experiencing two intermolecular forces, whereas the ethane is experiencing only one. That tells me that the methanol, the attractions between methanol molecules are stronger. So this is the one that will likely be a liquid. If the forces are stronger, it's going to be held together with more strength, and ethane is more likely to be a gas. There's a second problem here. Again, if you'd like to try it on your own, you can. I'm going to talk through it though. It says, the table below summarizes some physical properties of chlorine and hydrogen chloride. How can we use our understanding of intermolecular forces to account for the difference in enthalpy of vaporization? Now, enthalpy, that may be a word you don't know yet. Enthalpy is just a fancy word for heat. Enthalpy of vaporization means the heat required to vaporize, to boil these substances, okay? And again, it's a phase change, so we need to think about intermolecular forces that are at play here. So let's look at chlorine first. Cl2, totally nonpolar. So London dispersion forces only. HCl, also covalent, so it's going to definitely experience London dispersion forces, but it's also polar, so it will also experience dipole-dipole attraction. Okay, now, that's similar to what we saw in the problem above. However, I want you all to focus your attention on this column right here, okay? That delta H, that means heat. The heat required to vaporize these substances. And if you look at these numbers, it's showing us that chlorine requires more heat. And that might seem backwards to you, because chlorine only experiences LDFs. However, let's remember, what intermolecular force is the only one that is affected by size, or to be more specific, number of electrons? That would be London dispersion forces. Chlorine, Cl2, is a larger molecule. It has more electrons. It's more polarizable. There's that vocabulary word. HCl is a smaller molecule. So what this is saying to me is that even though HCl is experiencing more intermolecular forces, it's a smaller molecule. It's not as polarizable as chlorine. Chlorine being more polarizable, its London dispersion forces are stronger than both of the forces HCl is experiencing combined. Now that's unusual, and I will tell you that the AP exam loves questions like this, where what you would predict based on the intermolecular forces isn't exactly what the data shows, but the difference is the difference in size of these molecules. If you guys will notice the problem up above, look at that MW stands for molecular weight. This is showing us that these two molecules in that first example are pretty similar in their size. I mean, they have the same molar mass, so that's not really a factor in that one, whereas this question at the bottom, it is a factor. Size is a factor. All right, let's look at our final type of intermolecular force, hydrogen bonding. And guys, I put that word bonding in quotes, in quotation marks, because it is not actually a bond. It is still an intermolecular attraction. It's not a bond. And so that word bond is kind of a misnomer. But hydrogen bonding, our third and final type of intermolecular force, the strongest of the three, comes from when you have not just a covalent compound, not just a polar covalent compound, but it's more specific. It is experienced in molecules that have hydrogen, obviously, that's in the name, and one of the three highly electronegative elements, nitrogen, oxygen, or fluorine, NOF, or the FON elements. Okay, and this image on the right is showing you with those red dots some of the what would be considered hydrogen bonding, that hydrogen bonding attraction. Now there is a little bit of a stipulation with this intermolecular force. Hydrogen bonding, of course, involves hydrogen and these three highly electronegative elements. However, there is one further stipulation. Hydrogen in the molecule needs to actually be covalently bonded to N, O, or F. And let's look at these examples at the bottom of the slide here. Okay, Both of these compounds are covalent, so both of them are going to be experiencing LDFs. I'm going to write that down. Both of them are polar molecules, so they are both experiencing dipole-dipole attraction. Let me write that down. However, only one of them is experiencing hydrogen bonding, and maybe you can already sort of guess here. Remember, hydrogen has to be present, NO or F has to be present, but the final stipulation is that that hydrogen has to be chemically bonded to NO or F, and I can see that in this one. So this molecule on the right is experiencing hydrogen bonding. Whereas the molecule on the left, look at what the hydrogens are actually physically bonded to. They're bonded to carbon. That does not qualify this molecule for hydrogen bonding. The molecule on the left is experiencing LDFs and dipole-dipole only, whereas the molecule on the right is experiencing all three. And again, let's tie that back to things like melting point and boiling point. Likely, the molecule on the right would have higher melting and boiling points because it is experiencing more stronger attractions, intermolecular attractions. So we're going to play a little game here. Is this hydrogen bonding, yes or no? Okay, and I'm going to go in order. If you look at the little boxes, I'm going to go in order here. So let's look at box number 1 and the attraction that box is pointing to. Is it hydrogen bonding? No, it is not. Okay, it's pointing to a covalent bond between oxygen and hydrogen. So that's not hydrogen bonding. Hydrogen bonding is an intermolecular force. Okay, let's look at box number 2. It's between two molecules. Okay, that's good. It's between hydrogen and one of the FON elements. That's good. And look at what the hydrogen involved is actually bonded to. Also one of the FON elements. Box number 2 meets all of the requirements. So that is hydrogen bonding. Okay, let's come over to box 3 on the left here. Looks like it, right? It's between two separate molecules. That's good. It's between hydrogen and one of the FON elements. That's good. However, look at what the hydrogen that's involved. Look at what it's bonded to. It's bonded to carbon. Guys, that is not hydrogen bonding, and that is so tricky because it looks like it, but it's in fact not. Okay, let's come up to the top. All right, box number 4. Between two different molecules, check. It's between hydrogen and one of the FON elements, check. And look at what the hydrogen is actually bonded to, one of the FON elements, check. This is hydrogen bonding. Okay. Last one down at the bottom, box number 5. Now, this is a little bit odd because the hydrogen and the oxygen shown with box number 5, they are in fact actually part of the same molecule, but this is qualifying as an intermolecular force because it's not an actual, covalent bond here. So it meets that requirement. It is between H and one of the FON elements, but guys, again, look at what the H is bonded to. That is not hydrogen bonding. Okay, so you've got to be very careful. You'll see this in multiple choice a lot. Is this hydrogen bonding? Which of the following is an example of hydrogen bonding? That sort of thing. There is another type of interparticle attraction, and we will talk a little bit more about later in Unit 3. It's called an ion dipole force. And where this is going to come up is often when you're dissolving, let's say, an ionic solute in water, for example, like table salt, sodium chloride. you're going to see an attraction between the dissolved ions and the water molecules. Water is, of course, polar. This type of attraction, just for your information, is the strongest type of interparticle attraction. Okay, it is stronger than dipole-dipole, but we will discuss this ion-dipole attraction in a little bit more detail later on in this unit. So to kind of bring this a little bit together, we've talked about melting and boiling points, but there are some other things that are affected by the strength of intermolecular forces. Of course, melting and boiling points. Surface tension, you may have done that little experiment when you were younger where you get a paper clip to sort of sit on top of the surface of the water. Surface tension is the resistance to breaking the plane of water, okay? Heat of vaporization, we've talked about that. How much heat is required to boil a particular liquid? Viscosity is how thick a liquid is. Like, think of liquids like syrup and molasses or motor oil. These are very thick, viscous liquids. That's a factor affected by intermolecular forces. Vapor pressure is something we'll talk about a little later on in this unit, but it just means above any liquid there will be some vapor, some gas from that liquid. How much pressure does it have? Volatility is a liquid's ability to evaporate. When you go and get your flu shot in the wintertime and the nurse puts a little bit of alcohol on your arm before the injection, liquid alcohol evaporates very quickly. It's a very volatile liquid. These first 4 bullet points are properties that increase the stronger the forces are. The stronger the forces are, the higher the melting and boiling points will be, the greater the surface tension, the more heat required to vaporize, the more viscous the liquids will be. Whereas these other 2 at the bottom, again, we'll talk more about this later on in the unit, these properties decrease with stronger IMFs. The stronger the intermolecular forces, the less vapor there will be, so there's less pressure. The less likely a liquid is to evaporate with strong intermolecular forces. So let's kind of bring this all together, and then we'll end with an example problem. In general, if the size of the molecule is relatively similar, and you are asked to predict, let's say, which one has the higher boiling point, then in general, something that is experiencing London dispersion forces only is typically going to have a lower boiling point than something that is experiencing all 3 intermolecular forces. So in general, you can use just how many intermolecular forces are at play as a guide for things like melting, boiling point, heat of vaporization. Now that's if the size of the molecule is comparable. If the molecules are different, then it gets a little trickier. And we've seen examples of this. This is where sometimes the larger molecule is so polarizable that its London dispersion forces can be greater than things like dipole-dipole or hydrogen bonding attraction. So you have to be real careful in looking at the size of the molecule. Typically though, guys, if it is that second bullet point, if they are different, you won't be expected to predict which one has the higher boiling point. Typically they will show you which one has the higher boiling point, and you have to explain why. So last slide, guys, let's look at this example. Pause the video here if you want to try this one on your own. Otherwise, I'm going to talk through it. So we're given a table, And it says we are given the molecular structure and boiling points of CS2 and COS in terms of types and relative strengths of intermolecular forces in each compound. Explain why the boiling point of CS2 is higher than that of COS. Again, it has to do with boiling points, so guys, let's think strength of intermolecular force. CS2, I can see, is a completely symmetrical, nonpolar molecule, so it will experience LDFs only. COS, not symmetrical, so it will experience LDFs and dipole-dipole attraction. Okay, now, just based on what I've written right there, I would expect COS to have the higher boiling point. But I can see, if we look over on the right-hand side, that in fact CS2 has the higher boiling point. You would not be asked to predict that, and that's why they're telling you, hey, CS2 has the higher boiling point. Now let's explain why. We've talked through this, so even though CS2 is experiencing London dispersion forces only, it is a larger molecule with more electrons, and let's use that big vocabulary word. That makes CS2 the more polarizable molecule. So the London dispersion forces experienced by CS2 are in fact stronger than all of the forces combined from COS. That's how to answer a question like that. Whew, so that was a lot of information, but that is some of the most critical information in Unit 3. And as I said, Unit 3 is a big time heavy hitter on the AP exam. So I hope you all have learned a little something today, and I look forward to seeing you next time.